Hello, my name is Dmitry Bykov. I'm with the Samara University and Image Processing Systems Institute, and today I will talk about optical properties of resonant diffraction gratings with a slowly varying period. This is a brief outline of my talk. I will start from a motivation, then I will present the geometry of the structure and numerical methods which can be used to investigate its optical properties. In the main part of the talk, I will present simulation results and discussion. Resonant optical structures have many important applications, including sensors, laser resonators, nonlinear and magneto-optical devices, optical filters. Optical filters are particularly important in multi- and hyperspectral applications, where one needs a single device to select several wavelengths. This is usually achieved with a discrete set of resonant structures, each tuned at a particular wavelength. An alternative approach is the so-called linear variable filter, or LVF. It consists of a wedge cavity sandwiched between two Bragg mirrors. Different parts of such structure have different thicknesses and hence filter different wavelengths. In this talk I will discuss a different linear variable filter, which is based on a guided mode resonant grating with a varying period. Such structures are easy to fabricate, and there are many experimental works on this topic. However, theoretical and numerical treatment of these structures, which is the topic of this talk, is quite complicated. This slide shows the geometry of the considered structure. We have a waveguide layer sandwiched between a substrate and a diffraction grating. Its period varies linearly along the x direction. The period change rate is defined by the parameter alpha. Other parameters are presented on the slide. In order to simulate this structure, we adopt the so-called superperiod approach. We periodize the whole superstructure and optically isolate the adjacent periods with the use of perfectly matched layers. Since the period of the supercell can be quite large, it's worth discussing what numerical methods can we use to simulate the diffraction of light on such structures. If the period does not exceed a couple of hundreds of wavelengths, the first method to consider is the rigorous coupled wave analysis, RCWA, or which is the same Fourier model method, FMM. These methods allow calculating field distribution inside the structure when a plane wave is incident upon it. If we study resonant structures, we might want to calculate the eigenmodes of the structure, the field distribution of the eigenmode and the complex frequencies. This can be done by calculating the poles of the scattering matrix. If the period is very large, we cannot use RCWA because of enormous memory requirements and computation time. In this case, the use of a periodic Fourier model method might become favorable. This slide shows the basic idea behind the FMM and the AFMM. Within the FMM approach, we have a structure with a large period with respect to the x-axis. Within the AFMM approach, we rotate the structure by 90 degrees and optically isolate the adjacent periods as it is shown on the slide. In this case, the total period of the structure within the AFMM approach might become smaller compared to the FMM. As a result, at smaller period, this FMM approach works faster. However, when the superperiod is large, the AFMM approach shows better results. In order to investigate the optical properties of the varying period structure, we consider a monochromatic plane wave, which is normally incident on the structure. And we will be interested in the reflected field at different points along the structure, that is, at different values of x. The simplest approach to calculate the reflected field is the local periodic approximation. Under this approximation, we replace the varying period grating with the periodic one, having the period equal to the local period at the considered value of x. Then we simply use the RCWA to calculate the reflection coefficient at a wavelength of interest. This gives us the field spectrum shown on the slide. At each wavelength we see a pronounced resonance. These resonances appear at different spatial positions. This allows to use varying period gratings as linear variable filters in spectrometers and hyperspectral optical systems. The local periodic approximation is applicable only when the period changes slowly. In what follows, we will investigate the effects occurring when the period change rate is not that small. Let me show the field distribution, which was calculated rigorously using the RCWA within the supercell approach. As we can see from the slide, the resonant reflection peak is much broader now. Moreover, we see the secondary fringes that appear below the main peak. This plot was calculated when the period changes at a rate of 1 nanometer per micron. If we decrease this period change rate, the reflection peak will become sharper and sharper. If we further decrease the period change rate alpha, the reflected field distribution will converge to that predicted by the local periodic approximation. And on this slide, all the four previous plots are shown together. Once again we see that the line width of the resonances strongly depend on the period change rate. In order to investigate how the line shape is affected, let us consider vertical cross-sections of these figures. Considering vertical cross-sections means that we put a detector somewhere above the structure at a particular value of x. And then we illuminate the structure with the plane waves having different wavelengths to record the reflection spectrum. As we can see from the plots, the decrease in alpha results in decrease in the width of the resonant maxima. Besides, the shape of the resonance is different in the case when alpha is 0 and when it is non-zero. In the case of 0 alpha, the local periodic approximation takes place and the reflection spectrum takes simply Fano or almost Lorentzian line shape. This, however, is not the case for the non-zero alpha, when the line shape of the resonance is much more complicated. We have a central peak accompanied by a number of lower magnitude peaks located at shorter wavelength. This non-Fano line shape means that there are several eigenmodes which contribute to the reflection spectrum. Let us study these eigenmodes. We do this by considering a horizontal cross-section of the reflected field spectrum shown on the right. This cross-section is shown on the left with a red line. The dashed blue line shows the eigenmode field distribution, which was calculated as the pole of the scattering matrix of the considered structure. We can see that the maxima of these two lines almost coincide. This means that the optical properties of the considered structure can be described in terms of its eigenmodes. Let us note that the asymmetric line shape of the resonances, which we discussed earlier, is also manifested in the eigenmode field distribution. Indeed, we can see the central maxima of the eigenmode field, followed by a number of secondary maxima at positive values of x. To explain this asymmetric field distribution, let us consider the local dispersion of the eigenmodes of the considered structure. Let us choose some particular value of x, which is shown by the black arrow on the slide. At this point, we can replace our varying period structure with a periodic one, with its period equal to the local period at the marked point. The dispersion diagram for this periodic structure is shown on the slide. We can see two branches separated by a band gap, and the resonance which we studied earlier is marked with a black point. It is the even or symmetric or bright mode of the grating. Now let us study how the dispersion will change if we move towards the larger periods of the structure. What will happen if we increase the period? It turns out that the dispersion lines will move down as we move to the larger periods. Here, let me show it once again. Similarly, if we move to the shorter periods, the dispersion will go up. Now let us discuss what will happen if we try to excite the eigenmodes of the varying period structure by a plane wave. The wavelength of this plane wave is marked with a dashed black line on the upper plot. At some point of the structure, the local period will be such that the wave number of one of the diffraction orders will match the wave number of the eigenmodes supported by the structure. In this case, the mode excitation will take place. For the considered structure, this happened at the point marked by the black arrow, and the local period here equals to 195 nanometers. Once the mode is excited, the incident energy is efficiently coupled to the waveguide. Then, this energy will try to propagate to the left and to the right inside the waveguide. When the light propagates to the left, the local period decreases, and the considered wavelength turns out in the band gap of the local grating. Therefore, there is simply no mode to carry the energy, and the light will reflect to the right instead of propagating to the left. When the light propagates to the right, there appears two eigenmodes that can carry energy at the considered wavelength. These eigenmodes are shown with blue points on the figure. It is the interference of these two modes that gives the secondary peaks discussed above. Thus, the local photonic band structure allows to describe asymmetric field distribution of the eigenmodes and asymmetric line shape of the resonances in guided mode resonant gratings with varying period. In conclusion, we showed that the guided mode resonant grating with a varying period can be investigated numerically using the RCWA-based approach. Optical properties of such structures can be described in terms of complex frequency eigenmodes, which can be calculated as the poles of the scattering matrix. The resonances supported by this structure have pronounced asymmetric line shape, which can be described in terms of local photonic band structure. Thank you for your attention.